professor in the United States and also in mainland China. So it's our great pleasure to have Professor Wu to give this lecture. So unfortunately, he cannot come to attend the conference in person, but he's very kind to, he can give a talk online. So let's take this opportunity to give a big hand to welcome Professor Wu give this keynote talk. Yeah.
And I hope that in the future we'll have such opportunities. Good morning everyone. This is Dongrui Wu from the School of Artificial Intelligence and Automation, Huazhong University of Science and Technology in Wuhan. It's my great honor and a pleasure to give this talk on fuzzy logic for brain-computer interfaces. This is the outline of my talk. First, I will give introduction to brain-computer interfaces. CT also introduced the BCS in the first plenary talk. Next, I will introduce two pieces of our recent works on body size and signal processing for EEG feature extraction and body size and machine learning for EEG regression. Finally, conclusions and Q&A. A brain-computer interface is a direct communication pathway between the brain and an external device, which could be a computer, a robot, etc. It can be used for research, assist, augment, or repair cognitive or sensory motor functions. This is a flowchart of a closed-loop BCI system. We collect brain signals in various means, such as invisible spike signals, ECOG signals, or non-invisible EEG signals. Since generally these brain signals are very weak, we need to perform sophisticated signal processing to increase the signal-to-noise ratio of them. After that, we perform feature engineering and to reduce the dimensionality of the original features, and also to extract more meaningful features, more informative features. After that, we perform classification and regression to understand exactly what the brain signal means. Based on that, we can design controller to control external devices. Currently, brain-computer interfaces have been used for artificial vision, artificial cochlea, movement control, robot control, neural rehabilitation, games, and so on. Generally, there are two types of brain-computer interfaces. The first is invasive. Its advantage includes high signal-to-noise ratio. We know that there are billions of neurons in our brain, and current invasive sensors can collect a signal, spike signal from a single neuron. So it has very high signal-to-noise ratio, and the invasive BCS can be used to repair damaged vision, hearing, mobility, or language functions. But the main disadvantage of invasive BCIs are high cost and high risk, because generally we need to implant sensors into our brain, and after a certain time, for example, a couple of years, these sensors may degrade, and we need to remove old sensors and implant new sensors, which further increase the cost and the risk. The second type of BCS is non-invasive BCS. Their main advantages include low cost and low risk, because we only need to place EEG sensors on the scalp of human brain to collect non-invasive brain signals. It does not input any signal into our brain, and we do not need any surgery at all, so it is completely safe. But its main advantages include we need to perform user-specific calibration, and they are also subject to adversarial attacks and privacy leakage. In this talk, I will mainly introduce how we can use fuzzy set-based approaches to speed up user-specific calibration. For most non-invasive BCS, we are working on classification programs. Generally, there are three classical paradigms of non-invasive BCS. The first is called multi-imagery. It means the imagination of the movement of various body parts results in sensory motor context activation, which modulates sensory motor oscillation in the EEG. So when we imagine the movement of our right hand, generally a certain part on the left hemisphere of our brain will have energy change, and we can detect that from EEG signals. Then we can map this imagination into a command for external device, such as moving the wheelchair to the right, something like that. Generally, multi-imagery based BCS can be used in neural rehabilitation to speed up stroke rehabilitation. This is a short introduction of the principle of neural rehabilitation.
Rehabilitation training, the passive sequences when the patient is instructed to relax are alternated with active sequences when the patient is instructed to mentally imagine the movement of the carotid hand. The system detects patient's mental imagination of the movement based on the changes in EEG activity in the sensory motor cortical area. This is due to synchronization and desynchronization of the EEG rhythm. The patient is rewarded by the splint moving the wrist in a predefined way. The system allows to control the level of the required signal change during mental movement and hence to modify the difficulty of the training. The alternation of the sequences is maintained by vocal instructions.
Relax. Move.
According to the patient's state and needs, it is possible to individually set the training parameters, its length, number of repetitions, or their difficulty, and to change these parameters during the entire rehabilitation.
Okay, that's an example of multi-imagery BCI-based neural rehabilitation for strokes. The other two main paradigms of non-invasive BCS are based on video evoked potential, which is an electrical potential recorded after a subject is presented with a visual stimulus. There are two sub-paradigms. The first is called steady-state video evoked potentials, which are potentials generated by exciting the retina using video stimuli modulated at certain frequencies. So, its principle is that when we stare at a character flashing at a certain frequency, after a very short period of time, such as 1 or 2 seconds, the oscillation frequency of our EEG signal will approach the oscillation frequency of the character on the screen. So, by matching the main oscillation frequency of our EEG signals with the flashing frequency of the character on the screen, we can know which character the user wants to input. It is mostly used in EEG-based spirals. So this is a demonstration of SSVP spiral. So here, each character is flashing at a different frequency and phase. But the user stares at the letter he wants to input, and after a very short period of time, in this case I guess less than 1 second, we can decode which character he wants to input. Okay, the last paradigm is peak-handled event-related potential, which is a positive peak in the EEG signal at about 300 milliseconds after the appearance of a target stimuli or audible stimulus. This paradigm can also be used for text input. This is a simple demonstration. So here, each row or column of the keyboard is flashing randomly, and when user wants to input a certain character, we also need to stare at that character. When the row or column containing that character is flashed. Generally, we can observe a pitch temperature signal in the user's EEG signal. We determine which row and which column induces that EEG signal, and then the intersection will be the character fluence input. Generally, this paradigm is slower than SFVP-based surveillance, but it is also a feasible way for test input. Okay, we just introduced the three common classification-based BCI paradigms. For EEG-based BCS, there are several challenges which are limiting the current broad application of BCS. The first is sensor noise and degradation. This is hardware related and not the main focus of the talk here. The next is inter-subject differences, or sometimes called inter-subject or individual differences, which means EEG patterns for different subjects are different. The third is inter-subject variations, sometimes it's also called non-stationarity of EEG signals, which means EEG patterns for the same subject are different at a different scenario or time. As a result, it is very difficult, if not impossible, to design a BCI system with a fixed decoding algorithm and fixed parameters that can be optimal for all subjects. Generally, for a new subject, we need to perform subject-specific calculation, that is, to collect some subject-specific labeled data to tune the parameters of the classifiers to achieve good performance. But for real-world BCI systems, we need robust features and individualized and adaptive algorithms for better utility of such systems. So much effort of our lab is devoted into speeding up the calibration for EEG-based BCIs. In many other labs, most of our efforts were spent on classification programs in EEG-based BCIs. But in this talk, we consider regression programs in EEG-based BCIs. Why do we study such a program? First, because most BCI regression programs have been largely overlooked, but in EEG-based BCIs, there are many very useful regression applications. For example, when we want to estimate the cognitive status from EEG signal, which could be a value between 0 and 1, or behavioral status prediction. For example, EEG-based driver reaction time estimation, which should also be a continuous number, and also direct control applications such as BCI-based mouse cursor movement control, whose trajectory should be continuous. So there are many very important regression programs in BCIs. Next, I will introduce the first piece of work, body sets and signal processing for EEG feature extraction. And then these better features could be used in classifier for better performance. First, let's review the classical classification pipeline for multi-imagery-based BCIs. After EEG signal acquisition, first we need to perform temporal filtering to smooth the original EEG signal and also to remove some noise. This temporal filtering may include the notch filtering to remove the 50 or 60 Hz power line interference, and then bandpass filtering, such as, for example, 8 to 30 Hz to remove DC drift and high frequency noise. After that, we need to perform a spatial filtering, which is a very unique step for multi-imagery-based BCIs. Spatial filters include the basic ones, such as the common average referencing, Laplacian filters, and principal component analysis, and also more sophisticated ones, such as independent component analysis, XDOM, common spatial pattern etc. Especially for multi-imagery-based DCS, CSP, common spectral pattern filters, are very frequently used and they can achieve very good performance. In the next part of my talk, I will introduce how we can use party-set-based approach to extend common spatial filter for multi-imagery-based DCS to regression programs. After that, we perform feature engineering, that is to extract more informative and low-dimensional features from the original EEG signals. Feature engineering includes feature extraction and sometimes also feature selection, time domain, frequency domain, time frequency domain, remaining space, and top plot features to be used. The last step is the classification, which uses a machine learning algorithm to decode the EEG signal from the extracted features. So these common spatial filters are very effective for multi-imagery-based DCS. Here, we want to extend this spatial filtering approach to regression problem for EEGs. First, let me introduce the general idea of spatial filtering for supervised DCS classification. The goal here is to design a spatial filtering matrix W to increase the signal plus noise ratio for a certain class. Now here, we want to increase the signal to signal plus noise ratio. It is very similar to signal to noise ratio. So this spatial filtering matrix W is solved from this optimization problem. This TR is the space of the matrix. This X bar K is the mean EEG file of the case class. And in the denominator, this X is the mean EEG file of all EEG files, including the current class and all other classes. And this W star K can be solved by eigenvalue decomposition. So we first design a set of spatial filters for each class, and then the final spatial filtering matrix W star is the concatenation of all these W star for each individual class. So finally, we obtain a W star like this, and we apply this filtering matrix to the original EEG file Xn to obtain a new file Xn prime. After that, we will use Xn prime in all subsequent operations, including feature engineering and classification. We can safely discard the original Xn. So the goal of spatial filtering is to increase the signal-to-noise ratio of the filtered signals, and also to reduce the dimensionality of the filtered EEG channels. In this work, we want to extend the common spatial filter for multi-imagery-based DCS to supervise the DCS regression programs. For example, we want to estimate the tolerance level from filter's EEG signal, which is the regression problem. Note that in the original common spatial filtering computation, we need to compute the average, the mean EEG trail for each class, which is this X bar K in the numerator here. For classification problem, we can easily compute the mean EEG trail for each class, but for regression problems, we do not have the concept of a class, so it is very difficult to compute the numerator of the original equation. Here, we used a very simple idea of defining fuzzy sets for the training data. For example, we have a few labeled training data. The output would be the tolerance level of the driver, which is represented by this Y here. In its domain, we define several body sets. Usually, we use 3 body sets, meaning small, medium, and large. And then we observe, we check which training samples are falling into which body set. For example, for the first body set, we view that the first body class, we check which training samples belong to the first body class, and for each sample, its membership grade to that body class is denoted by this mu k here. Then we can compute the mean file for each for that body class using this equation. It is a weighted average, and the weight is the membership grade of the corresponding output in that body class. Note that this weight average weights on the input each sigma, not the output of y. Okay, in this way, we can approximately compute the mean EEG12 for each body class. After that, we can substitute this mean value into the original CSP formula to compute for the corresponding spatial filter vectors W star k. We repeat this process for each body class, and finally we can concatenate the spatial filter vector for each body class into a big filtering matrix, and the other steps are the same as those for classification problem. We just connect and multiplying the filtering matrix to the original EEG12 to obtain a new EEG12, and then to use that new EEG12 in feature engineering and classification. So this is a very simple extension of the original CSP filter filtering from classification to regression. We also have a very small improvement to the original filtering approaches. So here in the numerator, when we compute the mean EEG12 of each class, and then compute its mean covariance matrix, the formula is like this. It has, and in the numerator, we compute the mean covariance matrix of all EEG12 in this formula. So we can observe that in the numerator, we have an extra term which is not included in the numerator of this formula, and this extra term may degrade the performance of the final spatial filters. So we propose that we may be able to remove this extra term to achieve better spatial filtering performance. So in our improved spatial filtering approach for EEG-based regression problems, we had a different way to compute the mean covariance matrix in the numerator and the denominator. In the numerator, we just computed that using this very simple formula, and the denominator, which is the same as before. We have a scaling factor here, which is not important because it does not change the final spatial filters. The main difference is that we remove this interaction term for better performance. Finally, we performed experiments to validate the effectiveness of this simple spatial filtering approach for EEG-based regression programs. We used a dataset as first connected by CT and VL a few years ago when we had the joint project. It's EEG-based reaction time estimation in cycle motor witness task, PVT task. This PVT task is a sustained attention task that uses response time to measure the speed with which a subject responds to a visual stimulus. It is widely used, particularly by NASA, for its ease of scoring, simple metrics, convergent validity and free of learning effects. This is a short introduction to this paradigm.
This is the psychomotor vigilance test. It's a high precision response time test. A rectangle is presented on a black screen. When the numbers start counting inside the rectangle, the user should touch the screen. The subject should respond to each stimulus as fast as possible without false starts, which is responding to practice is available for this task.
Okay, this is just one particular implementation of this activity task. There could be other implementations, but the general principle is the same. For this problem, we first we compared several different feature extraction approaches. The first is the traditional approach. We extracted the theta and alpha power band features from the bandpass filtered EEG files. That is, we only perform the temporal filtering, but not spatial filtering. There were 62 channels in this dataset. For each channel, we extracted 2 power band features. So there is a total of 124 features in feature set 1. For feature set 2, we also extract the theta and alpha power band features from EEG trials, but these trials were spatially filtered by the direct extension approach. We defined 3 fuzzy sets for the response time and 21 spatial filters for each fuzzy class. So the spatial filtered signals had 3 dimensions. Here we deliberately used a large number of spatial filters to make the dimensionality of the feature here similar to the dimensionality of feature in the first feature set. We also constructed a third feature set. Here we extract the theta and alpha power band features from EEG trials, spatially filtered by the improved approach. Here we also had 126 features. By direct extension approach and the improved approach, we mean here the left part is the direct extension approach, and the right part is the improved approach. For the improved approach, we just remove the interaction term in the numeric. That's the only difference. But for both direct extension approach and improved approach, we use fuzzy set-based performance spatial filters. For classification, we tried 2 very simple but reliable approaches, including lasso, which is the linear regression, and k-nearest neighbors, which is nonlinear regression. Here is the main performance. We compute the root mean squared error of the estimations and also the correlation coefficients with the true reaction time. For each classifier, for each regression model, lasso and k-nearest neighbors, we compared the performance of these 3 different feature sets, FS1, 2, and 3. Here, for the average performance, it may not be easy to distinguish among these parts very clearly, but for their numerical values, we computed that the improved feature set reduces the root mean squared error by 10 to 20%, and also they increased the correlation coefficient by 20 to 85%. We have a range here because for different regression models, the improvements could be different. But for both regression models, the improved feature extraction approach can always outperform the direct feature extraction approach, and also the one without using any spatial filter. So as a simple conclusion here, we have demonstrated that by using fuzzy set-based approach to define the fuzzy classes, we can easily extract the performance spatial filtering, which is originally proposed for EEG-based classification problems, for regression problems for spatial filtering, and the resulting features can be more effective in binary regression. Next, we will introduce an approach for fuzzy set and machine learning for EEG regression programs. Many machine learning approaches have been used in EEG-based BCIs. The main goal is to minimize user-specific characteristic data. In our lab, we have applied different approaches, including transfer learning, deep learning, active learning, and ensemble learning. In this talk, I will mainly focus on transfer learning. The idea is to make use of useful information in general data, such as data from other subjects in the same task, or data from the same subject in similar tasks, etc., to facilitate the learning for a new subject. That is, we want to make use of data or knowledge from old subjects to speed up the calculation for a new subject. The main challenge is that the data distribution of different subjects are dramatically different due to individual differences. So there is an urgent need to remove the data distribution discrepancy among different subjects. If we cannot do that successfully, we may result in negative transfer. That is, using data from other subjects may decrease the performance of the classifier on a new subject instead of increasing it. In this work, we extended a transfer learning algorithm called online weight adaptation regularization or regression, which was published in 2016 with CT to regression programs. This is a very good transfer learning approach for classification programs. Here, we want, for the original classification program, we want to design a classifier denoted by this symbol F. By solving this optimization problem, this is a very complex optimization problem. It includes 5 terms. The first, here, this is the representation of our formulation for the regression problem. We want to solve a regression for the new subject from this optimization problem. It includes 5 terms. All 4 of these were inspired from the original classification transfer learning algorithm. Let me briefly explain the meaning of these 5 terms here. The first term is to minimize the loss on fitting the labeled sample in the source domain. So here, yi and xi are labeled data from the source domain from the old subjects. And the second term is to minimize the loss on fitting the labeled sample in the target domain. So here, yi and xi are a few very small number of labeled samples from the target domain from the new subject. Because this is a regression problem, we use mean squared error in the first 2 loss terms. And the third term is to minimize the distance between the marginal probabilities of the old and the new subjects. This term was borrowed from the original transfer learning algorithm for classification problem. There, we also needed to minimize the distance between the marginal probability distributions of different subjects. Because for classification and regression problems, the marginal probability distributions are computed in a safe way, so we can use the original formula directly. Then the fourth term, the one in the red rectangle, is to minimize the distance between the conditional probability distributions of the old subjects and the new subjects. For classification programs, usually we use the class conditional probability distribution, which is very easy to compute. But for regression programs, there is no concept of a class conditional probability. So we needed to have a new way to approximate this term. Otherwise, we cannot use this term in our optimization program. The last one, the fifth term, is a dedicated term for the regression problem. Because we observed that sometimes the regression model just output a constant which could have very small root mean squared error. but that is not meaningful. So the last term is used to enforce that the output is not a constant. Instead, it should have a high correlation with the original input. So the last term is used to maximize the correlation. In summary, for this regression program, we have these 5 terms serving different purposes. 4 terms are very easy to compute, but the 4th term, the conditional probability distribution alignment, is not easy to achieve for regression programs. This page explains how we solve that problem. For classification programs, these conditional probability distributions are conditioned on different classes, so they are easy to compute. But here, how to compute the CPD for regression programs? We still use the simple idea introduced in previous piece of work. For each output, we define for each subject we define some fuzzy sets. Here we also use the 3 fuzzy sets for simplicity. So we try to align the data falling into the first fuzzy set of subject 1 with the data falling into the first fuzzy set of subject 2. In this way, we can reduce the conditional probability distribution of the different subjects. So this is the general idea. It is very easy to implement. After we computing the conditional probability distributions, we can substitute this value into the previous optimization problem, and this problem has a closed form solution. So we also tested the performance of this simple approach in an experiment driver coordinates estimation. This data set was actually also from CT school. It is a suspended attention driving experiment, which includes 16 subjects, each performed 60 to 90 minutes driving. It's autonomous driving at 100 kilometers per hour on a street and empty highway. We had random late party events every 5 to 10 seconds. The response time was the actual response time, that is from the starting of this late party departure event to the first time point the user starts to turn his steering wheel, is converted to coordinates index between 0 and 1. We want to use EEG signals to estimate this coordinates index between 0 and 1. And the EEG signals were recorded by a 500 Hz 32-channel neuroscan system. Here are the main results. Again, we use the root mean squared error and the correlation coefficient to evaluate the performance. Our proposed approach called WAAR, SGS, and also WAAR. Here, this SGS means source domain selection. Because here we have 16 subjects, each time we use the 15 subjects as the source subjects to have the calibration for the new subject. Due to large individual differences, the responses of certain subjects may be dramatically different from others. So here, source domain selection is used to remove these dramatically different subjects. The experiment showed that our proposed WAAR and its source domain selection variant achieved a similar performance, especially for root mean squared errors. They are much better than other baselines, including TAMF, which is also a baseline we reported before. And also, our new approach converged very fast. That means from this figure, we can see that we only need 12 calibration trials, then its root mean squared error almost converges. So these results suggest that this new approach has very short calibration time and very good calibration performance. Finally, conclusions. There are some very important EEG-based BCI regression programs, including behavioral or cognitive status prediction or direct control applications. Challenges for EEG-based BCIs include EEG signals are very noisy, so we proposed a multi-set-based signal processing, actually spatial filtering approach to increase the signal-to-noise ratio, and after that we can expect more useful features. And also, to handle individual differences, we proposed a multi-set-based transfer learning algorithm to increase the estimation accuracy. In conclusion, multi-set can be integrated with the state-of-the-art signal processing and machine learning approach for EEG-based PCIs. Actually, in the recent 1 or 2 years, we are also developing new approaches using along this direction. We have some papers under review for new development here, and I hope that next time I can introduce the new results. Finally, a summary of the big picture of the research in our lab. Our lab is called Brain Computer Interface and Machine Learning Laboratory. We focus on accurate, secure, and privacy-free driven BCS. For accurate means accurate decoding. The main idea is to use transfer learning and non-data filtering approaches to speed up the calibration. Secure means EEG-based BCS are subject to adversarial attacks. So we developed different approaches to attack EEG-based BCS. That is, we can add a small perturbation to the user's input EEG signal to mislead the classifier to output the wrong decisions. This could be very dangerous. For example, the user may use his EEG signal to control a wheelchair. His original command is to move the wheelchair to the left, but after a small perturbation, the decoding output may be moving the wheelchair to the right. It may hit the wall or run into traffic, hurting the user. So we developed different approaches to attack EEG-based BCS, but in the past few years, we are more interested in how to defend against such attacks. So we developed the adversarial detection and training approaches for the adversarial security. The last piece is privacy protection. In EEG signals, in addition to these multi-imagery or SSVP information, there is also other private information that the user may not want to disclose, such as the user identity, emotion, gender, age, etc. They can also be mined from a user's original EEG signals. So we developed different approaches such as data perturbation and federated learning, etc., to achieve privacy protection. We have received some recognition in this direction. For example, we received the Best Paper Award from 2021 at Advanced on Nervous System and Rehabilitation Engineering. And last month, we also received 2 awards. One is Best Paper Award from Advanced on Biomedical Engineering, and also winner review award from ACA Journal of Medical Seneca. Our team also won 3 national championships in the past 4 years in China BCI competition, which is the highest level BCI competition in China. Okay, that's all for my talk today. Thank you very much again. And if you have any questions, I'll be happy to answer them. Thank you.
Yeah, thanks for Professor Wu's wonderful talk. Okay, so any questions to Professor Wu?
Hi, Professor Wu. I'm wondering about if you have tried to use the fuzzy features with multinomial regression because by the setup of your fuzzy membership function, it seems like it is more suitable to do a k-stage multinomial regression instead of linear regression.
Sorry, I cannot hear that question very clearly. Can you repeat that?
So can you hear us?
Yeah, I can hear you.
Okay.
So I want to ask about if you have tried to use multinomial regression using the fuzzy features, because by the setup of your fuzzy membership function, it seems like it is a discretized and it is having a ordinal relationship between the classes. So it seems to me it is more natural to use ordinal multinomial regression instead of linear.
That's a very good suggestion. Actually, this work was done a few years ago. There, we just tried to evaluate the effect of these newly featured. So we used very simple regression models. One is linear Lasso, the other is nonlinear KNN. But of course, we can try multinomial regression or more sophisticated regression approaches. Another reason we used these very simple regression models was that for PCR calibration programs, usually we have only a very small number of calibration samples. So if the model is too complex, it may easily overfit. So generally, we need to find a good compromise between the complexity of the model and also the performance of the generalization performance of the model.
Okay. Any other questions from Professor Wu? Okay. I have a maybe more basic question. Okay, on based on your experience. So since fuzzy logic needed human knowledge and the human experience. So can you share us, because the data driven, and how can we design such fuzzy membership, to the BCI either machine learning model or regression models, and in comparison with the common traditional statistical machine learning. So how can it improve, or how can we do that? For improve the performance. Based on your experience.
Okay, thank you very much, Leo, for the question. Actually, I have not considered that very carefully. But here, for example, in this work, we incorporate the human knowledge into the design of these membership functions in choosing the number of membership functions and its shape. Maybe the next one can be more, can illustrate this concept more easily. So, based on our experience, we only choose a small number of membership functions. In this case, only 3, and we also tested whether we can have performance improvements if we have 4, 5, or more membership functions, and they have very similar performance. And also, we based on the understanding of this problem, we designed the shape of these membership functions. For example, here we use traploid and triangular membership functions. Where should we place the endpoints of these membership functions? We just use the 5 percentile, 50 percentile, and 95 percentile of the value in the training data to determine the endpoints of these membership functions. So these are experience or knowledge-driven instead of purely data-driven prediction. I mean, using an optimization algorithm to tune the parameters of the language functions. So by incorporating this very simple knowledge, we can define the fuzzy classes, and they perform very well in the final regression program. I guess more sophisticated or richer knowledge can be integrated into this process. Well, recently we have another piece of work under review. There we have a very simple idea. So for a traditional regression program, we can use traditional algorithm to solve it. But in the optimization function, in the loss function, we also use fuzzy set to partition the output domain into a few fuzzy classes. And then we also include the loss term for the classification problem. That is, we include a few regularization terms on the classification problem to the regression objective function. And we found that generally this can also result in performance improvement. So I guess there are lots of different ways to incorporate knowledge into the design of these fuzzy sets. Well, we will try to do more in this direction, and I hope that I can have some new results to show you next time.
Okay, yeah. So many thanks for your illustration. Yeah, since I will ask this question because if we want to apply such technology to the smart healthcare or clinical problems, sometimes we need to rely on and based on the medical doctors, their experience and their knowledge. Yeah, so hopefully, we can have some more application, by these theoretical algorithms, for the further application. Yeah, thank you for your. Any other final? Okay, Yukai, Dr. Wang.
Hi, Dongrui, this is YK from UTS. So I have one question. As I understand from your fruitful presentation about the body system and the BCI. So in your talk, you also touched the privacy and the security issues. So from your perspective and the experience, do you have any suggestion to design the further BCI diagram and the machine learning model or deep learning model?
To the microphone, because the volume here is a little bit low.
Okay, so I can repeat again. So from your perspective, is there any better way to design the further BCI diagram as well as the machine learning model to meet the privacy and the security requirements in the near future?
Thank you very much for this question. Actually, for this morning and yesterday, I was at a meeting organized by the Natural Science Foundation of China on new paradigm for BCIs and new algorithm, large models, etc. And people are proposing different new paradigms for BCIs, including speech BCI, which is also a new direction in our lab, and also region-based BCI, and for the new decoding algorithms, including those based on large models, and also a new direction started in our lab about 2 years ago on non-data fusion-based decoding approaches for EEG-based BCIs. And also we need to consider different aspects of the decoding. In addition to the traditional accuracy, we should also consider its security and privacy protection ability. Especially privacy protection is a requirement by different laws, including General Data Protection Law of Europe and also Personal Interaction Protection Law in China. So I guess there is a large need for its accurate, secure, and privacy-free zeroing, decoding algorithm for EEG-based PCS, and also other forms of inputs such as apneas or cough signals, etc.
Thank you. Thank you.
Thank you.
Hello, Dongrui. This is Shu. So I have a question about the EEG foundation model since it's been recently brought in our field. So what do you foresee that fuzzy theory or fuzzy membership function can play in building EEG foundation models?
I have not used fuzzy set or fuzzy logic-based foundation models to decode the EEG signals, but recently we had some work on new approaches for optimizing fuzzy systems. We borrowed a lot of techniques from the optimization of neural networks, such as the mini-batch Gaussian descent, dropout. Of course, dropout cannot be directly used in fuzzy systems. So we, based on that idea, we proposed a new approach called Dongrui Wu to optimize fuzzy system, and also some ideas from the optimization of mixture of experts based on large language models, such as uniform representation, which is to force these experts to be competitive and also to cooperate with each other to achieve best performance. So we followed these ideas or techniques from the training of neural networks and large language models to the optimization of fuzzy systems and achieve the performance. Recently, we are thinking in another direction because the way to the computational formula for TSK fuzzy systems are actually very similar to the way in computing the attention mechanism in these large models. So we were considering whether these new ideas in attention mechanism can be used to improve the training and also maybe to inspire some new architecture for TSK fuzzy systems. We are still working on this direction. So if we can have some results here, I guess based on this, we can construct fuzzy logic or a hybrid of fuzzy logic and neural network large models, and then use them for EEG signal decoding. Thank you.
Okay, due to time constraint, yeah, so let's thanks Professor Wu give this wonderful talk. So Dongrui, can you see our conference room, please? You see everybody, many people, yeah.
I guess for the last talk on the last day, usually there are not so many audience. So I'm very excited to see we still have so many audience here. Thank you very much for your attention and the wonderful questions.
Okay, thank you. Yeah, so let's keep in touch. Yeah, so I will talk to you more about the future plan. Yeah, thank you. Thank you.
Okay,
okay, see you. Okay, yeah, so it's our closing remarks about the conference CSS and iFuzzy. Yeah, so our general chair iFuzzy Professor Yifang Zhong, can you say something? Yeah. 我们现在是最后的这个结语了哈，就闭幕结语，那我们就简单分享一下，看各位有没有什么，我看今天好像没有外景了哈。没有。那我们对简单的好，来我们请那个iFuzzy的 General Chair 说一点话的。看今天好像常多老师。
谢谢各位老师、各位同学的捧场。那我想接下来是我们有未来就是在台中这边，那就是继续CSS跟iFuzzy。那我想我们未来还是很快就会继续大家一起碰面。那谢谢大家的参加，谢谢。
我看现在有没有老师想那个，应该不会有啊，跟张文哲老师、梁胜富老师，哇，这个谢谢。然后我们顺便介绍几个老师给大家认识一下，然后还有这边还有这个。